This is an entry submitted in response to the 2013 IEEE APS Student Design Challenge Reconfigurable Antennas. This entry is submitted from the Huff Research Group within Texas A&M Electromagnetics and Microwaves Laboratory. Our entry is a reconfigurable antenna testbed, a low-cost educational system for electromagnetics, wireless communications, and electronics. Here is a concept overview of our testbed. Our system is based on pattern and polarization reconfigurable antennas. The antenna under test, or AUT, can be switched between two different polarization states and two different pattern states, which allow for broadside horizontal and fire horizontal and broadside vertical polarizations. The reference antenna can be switched between two different polarization states, allowing the system to perform both co-polarized and cross-polarized measurements without having to physically rotate the antenna. The two different antennas serve as the basis for the two different modules in the system. Our system takes advantage of the reconfigurability of both antennas in order to test antenna radiation patterns and evaluate conditions for reconfigurable performance in a system. Our system can be expanded to accommodate multiple antenna modules to examine other antenna-driven techniques, such as source localization. Our antenna design is based on two probe-fed linearly polarized microstrip patch antennas, with one of the antennas rotated 90 degrees around the x-axis. The radiating mechanism for the antennas is the fringing electric fields at the edges of the patch. These can be approximated as rectangular radiating slots in the ground plane. To build the cross dipole from the two patches are superimposed in the ground plane. The patches are reduced in width and overlaid at the probe position to combine the two polarizations into a single antenna. This decrease in width will create a substantial reduction in the radiation efficiency of these antennas compared to their typical patch counterparts. The two antennas are now shorted together. To isolate each polarization state, slots are made at the intersection of the narrow patches. RF pin diodes are placed between the gaps, allowing each polarization state to be selected independently of the orthogonally polarized state. To activate the pin diodes and select the polarization state, bias lines are added to the design. The bias lines are grounded for both RF and DC, so that the DC bias on the center conduction controls the state of the antennas. For the third configuration of the AUT, an extra length of narrow patch is added, which extends the patch antenna beyond a half wavelength and produces an end-fire pattern. A quarter-wave bias T is added to isolate the extended arm's DC control from the adjacent arm. Two modules were developed to accommodate these antennas. Each module consists of an antenna, either the AUT or the reference antenna, a biasing circuit, a Teensy 2.0++ microcontroller, and an XB Series 1 Pro wireless radio. The wireless radios communicate using the 802.15.4 protocol and operate in the 2.4 GHz ISM band. In order to communicate with the Java program, the reference antenna module is connected to the laptop over USB. Now, we will discuss the fabrication of the antennas. After simulating the two antenna designs in Anisoft HFSS, each design was placed on a PCB using KiCad. Each PCB contains all of the electronics for the modules on the back plane of the antenna, including the antenna biasing circuit, the XB radio, and the Teensy microcontroller. We fabricated the boards ourselves using a milling machine, but the design files can also be manufactured inexpensively by a PCB fabrication company. You can download the design files at the Huff Research Group Wiki or the APS competition site. Once our boards were fabricated, headers for the XB radios and the Teensy microcontroller were soldered onto the boards, along with other electronic components like voltage regulators and bias resistors. Through plotting radiation patterns, our system is able to demonstrate a wide range of antenna principles through radiation patterns alone. In addition, we are able to find the number of packets lost during a measurement routine. As the AUT rotates, it will transmit its current degree, configuration state, and number of packets sent back to the reference antenna. The Java program will use the RSSI data and configuration state to plot the radiation pattern in real time. The LEDs at the ends of the arms of the antenna will indicate the biasing of the antenna. Overall, the polarization and pattern reconfigurability of the antennas allow for a low-cost, easy-to-use measurement system that can be expanded to perform more advanced and dynamic tasks.